Okay, so let's get started now. Welcome everyone. Welcome everyone to the last SNAPP seminar of the season. Before we begin, here are a couple of announcements. The seminar for the second half of 2021 will start with the talk by Shipra Agarwal on July 19. In the meantime, you may enjoy the excellent speaker lineup for the Applied Probability Days from July 7 to 9. The link is given in the SNAPP website. In the academic year 21-22, Shivateja Maguluri will continue to be in the organizing committee as chair, and Jing Dong, Mariana Alvera Cravioto, Neil Walton, and Yuan Zong will be the new members. And Amber Puha will join the advisory board with the current members. Further details, including the full schedule of talks, are available in the SNAPP website. Now, a few routine details. The link to the slides of today's talk is available at the SNAPP website, and I'll also copy the link to the Zoom chat box soon. Please feel free to type your questions in the chat box. There will be a few short pauses during the talk when you can unmute yourself and ask the questions to the speaker, and then there will be a longer Q&A at the end of the talk. All right, it's our pleasure to have Gauri Joshi as our speaker today. Gauri is an assistant professor in the EC department at Carnegie Mellon University since September 2017. Before that, she worked as a research staff member at IBM. Gauri completed her PhD from MIT ECS in June 2016, advised by Professor Gregory Warnwell. This year, she received the NSF Career Award. Other than that, Gauri received the ACM Sigmatrix Best Paper Award in 2020, NSF CRII Award in 2018, IBM Faculty Research Award in 2017, Best Thesis Prize in Computer Science at MIT in 2012, and the Institute Gold Medal of IIT Bombay in 2010. Today, she'll talk about her recent work on tackling computational heterogeneity in federated learning. So without further ado, Gauri, the floor is yours.
Thank you very much. So first of all, thank you to the organizers for inviting me. I'm excited to talk about this work. And thank you, Debankur, for the generous introduction. So the work that I'm going to present today is a joint work with my PhD students who have led and done the amazing research that I'm going to present. So Jianyu Wong, Yeji Cho are the PhD students who led this work. Hao Liang, a master's student, also helped a lot with the experiments. And we also collaborated with Qinghua Liu and Professor Vince Poor from Princeton. So since this work is about federated learning, and federated learning is an emerging paradigm of machine learning training on edge devices. So some of you may not be familiar with federated learning, so I'll spend some time at the beginning of the talk introducing what is federated learning. And the main focus of this talk is about heterogeneity in federated learning. So heterogeneity, both in data as well as the computational capabilities of the edge devices, is a major challenge in federated learning. So I'm going to talk about two works on tackling computational heterogeneity. Firstly, heterogeneity due to devices having different speeds of computation, and secondly, due to the edge devices being only intermittently available for training. So with that plan for the talk, let me begin by first briefly introducing SGD, because when I say designing distributed training or federated training algorithms, what I really mean is stochastic gradient descent, because ML training today is pretty much synonymous to using SGD. It's the most commonly used optimization algorithm. For example, the backpropagation algorithm is a special case of SGD. At its core, SGD is a simple method which involves optimizing an objective function, f of x, as shown here. And in the context of machine learning, the objective function takes the form of the empirical risk function, shown here, where F is the sample loss for the nth data sample. So capital N here is the size of the training data set, and we're computing the per sample loss at each training data point and averaging them together. So that's the objective function. And SGD is an iterative algorithm. In most current implementations, a version of SGD called mini batch SGD is used, where in every iteration, you take the current version of the model, denoted by X, and move in the direction of a stochastic gradient, which is computed by drawing a mini batch of B samples and computing the per sample gradients for those B samples. So eta here denotes the learning rate, and this is the update rule used for SGD. So from this update rule, you can see that SGD is an inherently sequential algorithm. But for large data sets where, say, capital N is very large, it is prohibitively expensive to run SGD at a single node, because it would take a long time to go through the entire training data set, one mini batch at a time. So in most standard implementations, especially for large data sets, SGD is run in a distributed setting, where the task of computing gradients and updating the model is split across multiple worker nodes. So you have a central parameter server, which stores the current version of the model. And there are some worker nodes. These are typically servers in the cloud. And what we do is that we take the training data set, we shuffle it, and then split it equally across these worker nodes. And then SGD, or which is also called synchronous SGD in this setting, proceeds as follows. So in each iteration, these workers read the current version of the model, then they will compute gradients or mini batch gradients using their own partition of the data set. And then these gradients will be sent back to the parameter server, which will update the model using this update rule. So it will average the gradients together and update the model. So if we think about how this framework will scale with respect to the number of workers M, so of course, as you increase M, we'll process more data per iteration, but it can also hurt the speed at which we proceed, because as the number of workers increases, waiting for the slowest worker can be a challenge. Also, communication delays on these links can be an issue in frequently talking to the parameter server. So in recent years, there have been several works on improving scalability of this framework, and including some of our works on asynchronous SGD, overlap, or local update SGD, which I'm not going to talk about today, but if you're interested, I'll be happy to chat offline. So in spite of these improvements to the scalability of the parameter server framework, it has some inherent limitations. So first of all, these workers are cloud servers. So they are typically chosen to be homogeneous, and they're available throughout the training process. And secondly, which is more important, is that we assume that there is a centrally available training data set, which is available at the parameter server beforehand, then it is shuffled and then partitioned across the workers. And these assumptions break down in many modern applications where data is being collected at the edge, at devices like cell phones or tablets, IoT sensors, etc. So an example application of this is the next word prediction service, which is used in most smartphone keyboards. So smartphone keyboards, whenever somebody types a word on them, there's a service that predicts what is the next word that the user will type. And in order to train the language models that are used to predict the next word, you need data, which in this case, the training data is what the users are typing on their phones. So if we want to train such a language model that will work for millions of users, then a naive approach would be to have these users send their training data to the cloud server. But first of all, these users are operating on edge devices, which are resource limited. So sending raw data to the cloud is very expensive and slow. So this won't be possible and scalable if you have many devices. And secondly, as you could guess, since the training data involves what users are typing on their phones, there can be privacy laws that forbid sharing this data with foreign cloud servers. So these are some issues in just using the parameter server framework to train models on data that is being collected at edge devices. So this is where federated learning comes in. Federated learning is a new paradigm which was proposed in 2017, and it has gathered a lot of attention in the past few years. So this paradigm operates within the constraints, the communication and the privacy constraints. And the core idea is that the data stays on the device, whereas the model training is moved to the edge. So in federated learning, what we do is that each edge client will perform a few local SGD updates. So they will read the current version of the model, perform a few local SGD iterations. So these are not just gradient computation, but they are rather updates to the model. So each client will do many local updates. And then these updates will be aggregated by the central server. So why this is better in terms of communication efficiency is that the only thing that is shared on these communication links is the model, not the data. So sending the model can be much cheaper than data. And because we are not sharing the data, it also has better privacy guarantees. So of course, this is not fully private because the model itself can reveal sensitive information about the data. So designing better privacy preserving algorithms for this setting is an ongoing area of research. But this model is definitely communication efficient, and it is already being used in next word prediction on Android phones. So at a first glance, if you look at this picture, it might seem very similar to the data center setting. Like the only thing that is different is that these are edge devices instead of worker nodes. But there are some subtle yet important differences between the data center based training setting and this federated learning setting, which opens up some new challenges that we need to address in terms of algorithm design. So the first thing is that since the data is being collected at these clients and not shuffled and then partitioned using some central server, the data is highly heterogeneous, both in size and composition. Secondly, the computation speeds can be variable because some devices might be cell phones, some might be tablets, etc. So depending upon that, they can be faster or slower than others. Due to communication limitations, these clients have to do many local updates. So it won't be possible to deploy something like synchronous SGD in this setting because it would require frequent communication with the central server, which is not possible for resource limited devices. Then the scale of the system is just an order of magnitude higher. So in the data center setting, you can use maybe tens or hundreds of workers at most to run the distributed training in parallel. But here you can have thousands or even millions of geo-distributed client nodes. And because there are so many client devices, only a subset of them will be available for training at a given time. So not all of them participate in each training round. Right? So these are the main differences. Now let me explain more concretely what is the optimization or the objective function of federated learning and the standard Fed averaging algorithm that is used in practice. So here is the objective function of federated learning. There are actually two different levels of objectives. So there is a local objective function at each of these clients, which is denoted by Fi for the ith client. It is the empirical risk function computed for the data that is stored at that client, that is collected by that client. And then there is a global objective function, which the central server seeks to minimize. And this is a weighted average of the local objectives, where the weight is proportional to the size of the data at the ith client. So you might wonder, why is this weight chosen as PI? Or the fraction of data size? The reason is that we want to emulate centralized training here. So if hypothetically all the data was sent to the central server, then this would be the objective function at the central server. So in order to emulate that, we set this weight to be PI. As you can see from this setup, the local and global objectives can be very different depending upon the heterogeneity in these data sets. And this can raise some issues for algorithms, convergence, and consistency, as we will see in the rest of the talk. But the main goal that we are going to focus on here is that we want to train a single global model that minimizes this global objective. So that's the goal that we're going to focus on. There are some recent works that study variants of this, where you're trying to train personalized models at each of these clients, but I'm going to focus on training one single global model for the purpose of this talk. So this is the objective function. Next, let me explain the algorithm, which is used to minimize this objective function. This is the standard federated averaging algorithm. So this algorithm is divided into communication rounds, where in each round, these clients which are available at the time get the current version of the model. Then they will perform tau local SGD updates. And because they have different data sets, they will end up with different versions of the model after those tau steps. And then these models will be sent back to the central server, which will aggregate them in proportion of the data set sizes. So it will just average these model parameter vectors in proportion of PI to get the updated global model. And then this process will repeat. So this is the algorithm. Now, what we want to understand in this talk is, how does this algorithm work in the presence of data and computational heterogeneity? Can it cause some convergence issues or consistency issues? So in that light, the goal of this talk is to highlight challenges that arise due to such heterogeneity. So first, we will talk about data heterogeneity. In particular, how does the choice of tau affect convergence? And then we'll talk about two forms of computational heterogeneity. First is where tau varies across clients, and second is, how does the choice of the clients that participate in each round affect convergence? So data heterogeneity, I'm going to cover only briefly to give you an intuition about how it affects convergence. But the main part of this talk will be focused on computational heterogeneity. Right? So with that plan, let me talk about data heterogeneity, and I'll pause after that to take questions. So to understand how tau affects convergence, let's consider a very simple example. There's just two clients, and these two clients have a unique local minimum, x1 star and x2 star respectively for the two clients. And x star supposes the unique global minimum. And this is the current version of the model which we start with. So our goal is that this model should reach the global minimum through the federated averaging algorithm. So if we set tau equal to 1, then what will happen is that in each round, the clients do one local update according to their local objective function. So these updates will roughly move towards x1 star and x2 star. And then these updates are averaged to get the new global model. So if we continue this process, we will make gradual progress, and we can show that this algorithm is actually equivalent to synchronous SGD. And if we choose the learning rate carefully, it can converge to the global model x star. So tau equal to 1 is not a problem. It's just equivalent to doing SGD in a distributed setting. Now let's talk about what happens if tau is very large, which is actually what happens in practice because of communication limitations. So we don't want to communicate so frequently. We want to shift more computation locally to the clients. So if these clients do many local updates, then in each round, they will reach close to their own local optimum, x1 star and x2 star. And if we average those, we'll get this global model. So it seems as if we are making swift progress towards the global optimum x star, which is what we want to reach. But an issue here is that once we reach here, if we take another communication round where the clients do many local updates, then they will go back towards their own local optimum value. And we are basically stuck here. So we are stuck at a point which is the weighted average of the local optima, which may not match with the global optimum x star. So large tau can lead to an inconsistent solution, which differs from the local optimum x star. More formally, so I hope this gives you an intuitive idea of how tau affects convergence. So more formally, in recent years, our work and actually many other works have analyzed the convergence of local update or federated averaging SGD to find out how exactly tau affects convergence. And the error bound is of this form, where the first term decreases with tau. T is the number of rounds that we complete. So tau is in the denominator here because in each round, if there's a larger tau, you do more updates in total. So the first term goes down. The second term actually increases with tau. So this is the term that arises because we are doing multiple local updates. If tau is equal to 1, then this will just disappear. And this term also increases with the amount of data heterogeneity, which is denoted by kappa. I'm not going to formally define kappa here. It's a measure of dissimilarity of the local objective functions. So if we look at the training loss versus the number of rounds, then having a large value of tau can be good at the beginning because you make faster progress in terms of the number of communication rounds. But then at the end, we will end up with this additional error term. So what are some solutions to addressing this? This problem caused by data heterogeneity has been tackled in many recent works. So some examples of methods are proximal methods that pull back the client models, that don't allow them to stray too far away from the global model. Or adaptive methods as proposed in one of our previous works that start off with a large value of tau and then reduce it so that we get both fast conversions at the beginning as well as a low error flow. But the bottom line is that data heterogeneity, although it is an issue if tau is large, can be tackled by either decaying the learning rate effectively, decaying tau, using adaptive tau schedules, etc. So this was about data heterogeneity. Next, I'll talk about how data heterogeneity coupled with computational heterogeneity can be quite a big problem. So let me pause here and take questions if there are any questions.
There is one question in the chat box. Mauli, do you want to go ahead, ask the question? Okay, so let me read the question. So clients have the computational power of the edge compute for SGD.
Sorry, I did not get the question.
So,
could you repeat again?
Do the clients have the computational power of edge to edge compute for SGD?
Oh, I see. So I guess the rephrasing what you want to ask is, are these clients capable enough to do SGD locally?
Yes, yeah, correct.
Yes, so this is often deployed on smartphones. So smartphones are equipped to do SGD locally. However, there is some limit on the size of the neural networks that you can use here. So these federated averaging algorithms currently are used for medium-sized networks. If the network is very large, then these edge clients may not be able to handle it. So I hope that answers your question. Thanks.
I have a quick question.
Uh-huh.
So when you initially talked about distributed optimization, you didn't have the weights in the objective, but in federated learning, you had the weights. So why is that?
Oh, so the reason we have the weights here is because the size of the data is different at each client.
So are you assuming that in the distributed optimization setting, the size was the same?
Yeah.
Oh, okay.
Yeah. So if you have evenly partitioned it, then you can just average uniformly. But since the size of the data is different, then we want to weigh the larger data set with a higher weight.
Okay, thanks.
That's it.
Hi, I had a follow-up question to my previous question.
Mm-hmm.
You were also making a point about the difference between data center networks and let's say the communication sort of network, the phone sort of. There, in some of the networking devices have a limited budget in terms of computation because obviously they want to switch packets. So, I mean, that's the reason, that was the context of my question. How much budget can be allocated for doing, I would say, more sophisticated computation at the edge. So,
Oh, so let me understand. So are you talking about the communication link? Or
no, I mean, at the router itself to do those calculations. By the way, I don't want to, we can discuss that later. If it's a more
okay, sure. Yeah, so maybe we can discuss offline, but a quick answer is that we are thinking about this at the application layer. So the networking layers are hidden under.
We'll take it offline. So.
Okay, sounds good. Thanks. All right, so let me move on to the next part of the talk, which is about computational heterogeneity. So this was a paper in New Trips last year. We came up with a way to fix consistency issues. So first, let me explain where computational heterogeneity can come from naturally in federated learning. So initially, when I described to you the federated averaging algorithm, I said that each client does the same number of local updates, which is tau. But in many implementations that are deployed already, clients actually do the same number of local epochs, not the same number of local updates. So this is just the way it is implemented. And this can cause an imbalance in the number of local updates because epoch means a traversal of the local training data set. So clients which have more local data will do more local updates proportional to their data set size, and clients with less local data will do fewer local updates. So this can cause a consistent difference in the number of local updates that each client is doing. An alternate way to run federated training, which is actually quite straggler resilient, is that instead of fixing the number of local updates that each client can do, and then slow clients being stragglers, we could instead fix a time window and then allow faster clients to do more local updates within that window, slower clients to do less local updates. In general, as many updates as they can. And this can also cause heterogeneity, as you can see. Finally, even if the number of local updates is the same across the clients, they may use different local optimizers. So far, I only talked about using vanilla SGD to do the local updates, but they may use something like an adaptive optimizer, Adagrad or Adam, or different learning rates, maybe different momentum values locally. And all of these will result in heterogeneous local progress. So such heterogeneity already exists in current implementations, but the algorithms that are used currently do not consider this heterogeneity. They just use the standard federated averaging setting. So this can be problematic because heterogeneous local progress leads to optimizing a wrong objective function. So let me explain that using an example. So let's consider again an example of just two clients, the same picture that we had before. So this is the global optimum that we want to reach. These are the local optima at the two clients. And in the homogeneous setting, if you have the same number of local updates, then this will be the global model. So this is how we will proceed. But in the heterogeneous setting, suppose the first client does many local updates, whereas the second client does just one local update. Then the averaged model will get skewed towards the first client. And this will happen in every communication round. So the solution will also get biased towards the client which has more local updates. And this bias cannot be just fixed by reducing the learning rate or other techniques that are used to tackle data heterogeneity. So to understand what effect this heterogeneity has, we proposed in our work a generalized version of the federated averaging algorithm. And this generalized version helped us understand that in the homogeneous setting, what we end up minimizing or we end up finding the stationary point of is this global objective, which we intended to optimize. Whereas if you have this heterogeneous setting and if we run federated averaging algorithm as is, then we end up minimizing a mismatched surrogate objective, which is given by f tilde as shown here. So the thing that is changing here is the weight assigned to the ith client. So by just averaging these local updates in proportion of pi without considering that some clients did more updates, you are implicitly giving a higher weight to a client that has more local updates. So this objective can be arbitrarily different from the global objective. It only matches with the global objective when all the tau i's are the same. Otherwise, it can be different from the global objective. So this is what we call the objective inconsistency problem. So how do we solve this problem? You can see that the issue is coming from the way these local objective functions are averaged. So the solution will also likely be in terms of adjusting the averaging weights. But how do we adjust the averaging weights? To understand that, let me tell you about the generalized version of the federated averaging algorithm. And that will immediately reveal the correction that we need to do. So to recall, this is the federated averaging update rule, which takes the current version of the global model. We start from here. Each client does some local updates. The accumulated local update, or the sum of these local gradients computed at different versions of the model. So the sequence of gradients, if we take a sum, we'll get this blue dotted vector, which we denote by delta I. So this is called the accumulated local update at the ith client. So these accumulated local updates are averaged in proportion of pi in the federated averaging algorithm. So in the generalized version, the first thing that we change is that we allow this accumulated update to be an arbitrary linear combination of the local gradients. So instead of just being a sum, this is a linear combination of the gradients where AI, the weights of the linear combination can be put in a vector AI, and the GIs can be stacked into a matrix GI and written compactly like this. So that's the only change. You can see that this becomes a special case. If all the elements of AI are equal, you go back to the original federated averaging setting. So the reason this is interesting and important is because by setting different values of AI, we can control the type of local optimizer at the clients. So AI changes the weights to different gradients in this sequence at the client. So many local optimizers actually satisfy this linear combination update form. So if you do proximal local updates where the client's update is being pulled back using some regularization term, then AI becomes like this. If you do, say, momentum SGD locally instead of vanilla SGD, then AI becomes this vector where beta is the momentum term. So this linear combination format actually helps us subsume many existing local SGD algorithms. And note that AI can even be different for different clients. So one client can use vanilla SGD, one client can use momentum SGD, etc. They could even use different learning rates. So all of that can also be subsumed in this form. So this is one generalization. The second thing that we changed is that instead of the central server averaging, taking a weighted average of these delta i's, the accumulated local updates, we consider that these clients will normalize their accumulated updates by the L1 norm of AI. So this doesn't change much. It just changes it just scales down what the clients are sending. And then the server can also set a weight assigned to each of these updates in a different way. So instead of PI, we allow this to be any general weight WI. So putting this together, the generalized update rule is as shown over here, where let's look at each of the different elements. The first thing is the normalized gradient. So this is the normalized accumulated local update that we have. So suppose you have this sequence of gradients and the blue arrow is the delta I. Then the green arrow here is the linear combination of these gradients, which we call the normalized gradient. So that's the green colored arrow. The second parameter here, which we can freely choose, is the aggregation weights, WI, which are assigned to each of the clients. So these aggregation weights, they are used to average these normalized updates sent by the clients. So they can control the direction of this global update that we make, the direction of these this orange arrow. And finally, there's another parameter, tau effective, which we call the effective steps per round. So this just controls the magnitude of the global update. So you can scale up or down this arrow depending upon tau effective. You can think of this like a global learning rate. So this avoids slowdown because of normalization of the updates. So in this generalized update rule, what we can show is that this ends up minimizing a surrogate objective function f tilde, which is a weighted average of the local objectives, but the weights now are WI, which are our aggregation weights. So there are several special cases of this generalized algorithm. One special case is just vanilla federated averaging, where the normalized gradient is just corresponding to AI being 1 over tau for all the elements of the gradient vector. And the aggregation weights in the case of vanilla federated averaging end up being this. Because so this is the weight applied to the normalized gradient. That's why instead of PI, we have PI tau I in the numerator. And the effective steps per round is just the weighted average of the local updates that are done at different clients. So by this general analysis framework, you can see that the surrogate objective is clearly mismatching with the global objective. And this point of view also suggests a simple fix to the consistency problem. All we have to do is take this WI and set it to PI. So that's what is at the core of our proposed FedNova algorithm. So we put any algorithm in this generalized or normalized averaging framework and then set WI to PI. So that will ensure that the surrogate objective function matches with the global objective. So let me show you an example of how we would use this to fix the vanilla federated averaging algorithm. So on the left-hand side, I'm showing just the vanilla federated averaging update. Here, we are taking an average of these accumulated updates. Instead, in FedNova, we'll take each update, this blue arrow, and then we'll divide it by the number of local updates. So this blue arrow is divided by 4 to get this green arrow. This blue arrow is divided by 2 to get this green arrow. And then we are going to average these normalized updates to get the global update. And this weight assigned to each of the normalized updates is just PI. So Wi is set to pi. And this will ensure that our surrogate objective is equivalent to the global objective. So this is the intuition. More formally, we present a convergence analysis of this generalized framework, and it gives an error bound, which is of this form. The first term here is a vanishing error term, which decays as we decay the learning rate. But the second term here is what comes because of the objective inconsistency. So this term is 0 in one of two cases, either if there's no data heterogeneity, that is this kappa is 0, or if the aggregation weights Wi are correctly set to pi so that this numerator disappears. So besides proposing the federated Fed-Nova algorithm, this analysis also gives some new insights on the convergence of existing algorithms, but I'll not talk about that for now. So finally, let me show you some experimental results on how Fed-Nova performs as compared to other methods. So this is federated averaging. This is another an existing algorithm, FedProx, which does proximal local updates. And the red color plot shows Fed-Nova. So what we can see is that both FedAvg and FedProx suffer from the objective inconsistency problem. So FedProx tries to reduce that inconsistency, but Fed-Nova actually eliminates that inconsistency, and we will get conversions to the true stationary point of the global objective if we decay learning rate accordingly in the standard manner. Another thing is that because Fed-Nova works with different local optimizers, all that we are changing are these aggregation weights. It can be used with different client optimizers, and it can give almost a 8 to 10% accuracy improvement. So the first column here shows averaging according to Fed averaging. The second column just shows this corrected Fed-Nova averaging with different client optimizers, and we can see quite a big test accuracy improvement. So this was about computational heterogeneity arising from the clients doing different numbers of local updates. In the last part of the talk, I'll mention what happens when we have intermittent client availability. But let me pause again. I can take more questions if there are any.
I have a question.
Mm-hmm.
So in this part, you're basically addressing the computational heterogeneity, right? So there's some guys that are fast, there's some guys that are slow. So a naive thing to do would be so let's say the slow guy can only do 2 steps. Then I'll make everybody just do 2 steps, and then they'll be sitting idle otherwise. So this is a very dumb idea, right? So how does your rate of convergence compare to the rate of convergence using the naive approach?
That's a good question. So that's actually one of the baselines that we did compare with. So if you just slow down everybody, then you do less local steps per round. So the effective number of local steps per round reduces. Right. So this tau bar that I showed earlier.
Tau bar. Okay.
Yeah. So tau bar becomes minimum of tau I in the algorithm that you are proposing.
Okay.
Whereas here we can choose this freely. So we choose it to be the average of the tau i's.
I see.
So we can show that because it doesn't slow down everybody, it actually gives better conversions.
Okay, got it. Thanks.
Yeah. Convergence when measured in terms of communication rounds.
There is one more question.
Yeah. Gauri, great talk. I have one question. So what is your assumption on the structure of objective function? So even if the objective function is non-convex, right, even the centralized algorithm may not converge to the global minimum.
Yes. Yeah, that's a good question. So I did not show the details here. So in the papers, we have convergence analysis, both for the cases where the objective function is smooth and strongly convex, as well as cases where the objective function can be non-convex, but it is smooth. So in the second case, when it is non-convex, as you correctly point out, it's not guaranteed that you'll reach the global optimum. So the convergence results are in terms of reaching a stationary point of that objective, not the global optimum.
Okay. Okay. Yeah. Thank you.
Any other questions? Okay, so do I have enough time left? I think there are 10-15 minutes, right?
15 minutes, yeah.
Yeah, I think that should be enough.
So may I follow up on this question?
Mm-hmm.
So in the case, the global, even for the global centralized algorithm, you converge to a stationary point. Then how do you know which one, local minima versus global minima on the stationary point, which one is better? Right? You have different devices, they converge to different local minima or local stationary points. How do you know which one is better?
Yeah. So in these deep learning works, there's no guarantee. Like we don't know which one is better. So we just reach some stationary point and hope that that is better. So there are lots of works recently in deep learning that like try to understand what the quality of the stationary points that we converge to, and in some cases you can show that they actually are good stationary points. So in our work we don't go into that because we are not making any like assumptions on the type of neural network or the type of objective function that we have. So there are no guarantees as such on the quality of the stationary points.
So the question is how, when you do aggregation, right? Or after you do aggregation, which way would it be better?
So empirically, this is what we've observed in experiments, is that if you do local update SGD like this with clients doing not just gradient computation, but many local SGD steps, then we end up with a slightly higher test accuracy in some cases. That's because there's some inherent exploration of the loss landscape that happens because each client does, more local updates in their own basin. But this is just empirical.
When the aggregation, you do better, slightly better empirically. Yeah. Okay.
Yeah, if you do aggregation in this way, you can do slightly better.
Okay, got it. Okay, thank you, Gauri. Yeah.
Sure. Thanks for the question. All right, so let me go to the last part of the talk. Here, I'll consider the case where only a subset of clients participate in each round. And we'll talk about how to choose that subset of clients. And I'll propose a client selection strategy, which is inspired by the power of choice load balancing strategy that's used in queuing systems. Let me first introduce why we need client selection. So as I mentioned before, there can be thousands or millions of these edge clients. And because they may be only intermittently available, and because of communication limitations, only a subset of them will participate in each round. So effectively, if we have a subset S of clients participating, then we are optimizing this surrogate objective function in the round because it's just a sum of the selected clients' local objective functions. So how do we do client selection in order for this surrogate objective to be consistent with the global objective? In most works recently, we do something called unbiased selection, where we can just sample clients at random such that client K is assigned a probability pk of being chosen. And then if we do sampling in this way, we can show that the expected value of this surrogate objective, expectation taken over the sampling, is equal to the global objective function. So by doing unbiased client selection, we can ensure that we will, on average, optimize the global objective function, which is the sum of all the clients' local objectives. So most works in federated learning consider unbiased client selection like this, and prior results on full client participation can also be extended to this partial client participation setting. So in fact, the FedNova result that I showed earlier, we derive it for the full client participation setting, but then also show that it can be extended to this unbiased client selection setting. But what I want to ask here is the question that, is it necessary that we should do unbiased selection? What if we preferentially select clients with high local losses? Because we are minimizing this sum. What if we try to choose clients which have high values of Fi more often, such that we reduce this global objective faster? So let's see through an example whether that can help. This is a toy example of just two clients. Their objective functions are shown in blue and green, respectively. And the red color plot here shows the global objective, which is the average of F1 and F2. So suppose only one client is chosen in each round. And if we do this client selection at random, then we can say start at this point, some arbitrary point in this space. And in the first two rounds, suppose we choose client 2, so then we will move downwards on F2. And then if we move to client 1, then in the next two rounds, suppose we choose client 1, then we optimize this blue color objective function. So we'll start from this point vertically and then go towards F1's local minimum. And then we might select client 2 again. So we'll end up going back here and then like kind of going in a loop. But because this process is done at random and not in an adversarial manner, eventually we can reach the stationary point of the f of x, the global objective. So this unbiased client selection will work, but it can take longer because of this kind of looping issue. Next, let's see what happens if we bias the selection towards high loss clients. So now my selection strategy is going to be at every point. I'll check whether F1 is higher or F2 is higher. And if F1 is less than F2, then I'll always select client 2. If F1 is greater than F2, then I'll always select client 1. So since I'm here where F2 is greater, so I'm going to continue selecting client 2 until I cross this point, after which I will select client 1. So if we do that, you can see that in the same 5 steps, we can reach closer to the global objective function. So this is just an illustration, like unbiased client selection could also, have a better sequence and reach here, but this is just to illustrate that biased client selection can actually help. So biased client selection can give faster convergence because we are quickly minimizing the high loss clients' objectives. But on the other hand, will this cause too much selection skew? So what if we keep on selecting clients that have high loss and then we just ignore other clients that have low loss? Can that cause bias in the solution? So to understand that, we can come up with a metric that measures the amount of skew in the selection strategy. So if you have a selection strategy pi and the selected clients S pi x, because the selection also depends on the current version of the model in the case of bias selection, then we can define selection skew as this quantity. And there are 2 other forms of this quantity that appear in the convergence analysis. So I'm not going to go into the details of this expression, but this term rho, all you need to know for the purpose of this talk is that this rho is equal to 1 if you're doing unbiased client selection. If you do biased client selection where you skew towards higher loss clients, then this rho increases. It goes higher than 1. If you bias towards lower loss clients, then it goes lower than 1. And then we can analyze the convergence of any arbitrary client selection strategy in terms of these selection skew metrics. So this is the rough format of the convergence bound. All the constants I've dropped here for brevity. The main thing to note here is that in the first term, which corresponds to the convergence rate, you get this rho. So if there's a higher bias, higher selection skew, then we get faster convergence. But if there is a selection bias, then we also get this non-vanishing error term in the second term of the error bound. And this non-vanishing error actually increases with the amount of data heterogeneity. So in this paper, data heterogeneity is measured in terms of the parameter gamma. If there is no data heterogeneity, then the second term just drops off. But in presence of data heterogeneity, you do get a non-vanishing bias. So what we want to do is to come up with a selection strategy that finds a good sweet spot between this. So we want fast convergence, but we also don't want this second term to blow up. So what we propose is based on the power of choice load balancing framework. So this is the client selection strategy that we propose. Step one is that out of the total set of clients, we can choose a candidate set A of size D, where client K is chosen with probability Pk. And then these chosen or candidate clients will estimate their local losses Fi and send them to the central server, which will then compare the local losses. And then it's going to select the M clients out of these D that have the largest value of the local losses. So in this case, suppose client 3 has the highest loss, then we can select client 3. So observe that the parameter D can be used to tune and find a trade-off between convergence rate and the bias. So if we set D equal to M is the number of clients that we want to choose, then this is equal to unbiased client selection. But if we increase D, then we are skewing more and more towards high loss clients. So this idea is not new in SGD in general. There have been bias sampling strategies like this that are proposed for single node SGD training. So we are applying it here in the federated learning context. So these are some plots that show how the power of D scheme performs. As you increase the value of D, we can see that the convergence is faster, but then we do get a slightly higher error flow because of the selection bias. So one may come up with also adaptive schemes that have a large value of D at the beginning and reduce D as we go on. We have one such adaptive scheme in the paper. I'm not going to show it here. But in general, increasing D gives faster conversions, but a slightly higher solution bias. Another thing you might note is that this step 2 can be somewhat expensive because these clients are estimating local losses and sending it to the central server. So we also came up with some computation and communication efficient variants of step 2 that will in fact even avoid communication, this additional round of communication altogether. And these variants, I'm showing the results for the variants here. They do almost as well as the vanilla power of D strategy. So these variants C power D and R power D do almost as well. And another interesting phenomena that we observed is that as you increase the amount of data heterogeneity, these biased selection strategies in fact do better in terms of speeding up convergence and test accuracy. So the solution bias does not, which we see in theory, does not seem to affect the performance as much in practice. So with that, I'm going to wrap up and just summarize. So I hope that this talk gave you a flavor of the problems and challenges in federated learning. In particular, here we talked about data heterogeneity, computational speed heterogeneity, and intermittent client availability. But there are many other interesting and open problems. There are some very interesting recent works on personalization, where we want to train personalized models at each of these clients. There's also fairness and robustness issues here. So if one client is participating more often in training, then the global model can get skewed towards that client. Or the global model can also get skewed towards clients that have more data. So you can also adjust the objective function to introduce fairness to low data or slower clients. You can also come up with ways to improve robustness. In fact, the client selection strategy that we did, that we proposed, can be used to incorporate fairness and robustness in some way. I'm going to skip that over here. And privacy is, of course, a major concern, and there are many other open challenges. So thank you, everyone, for the attention. I'll just flash the archive links to the papers that we covered in this talk. I mainly focused on the first two papers. And then there are other papers on distributed SGD from my group if you're interested in looking at it. Thank you.
Let's all thank the speaker for the excellent talk. So if there is a very small, quick question, then maybe we can go ahead. Okay, if not, let's thank Gauri again.
Thank you, everyone.
Let's stop the recording.
Can I now ask a couple questions because they may not be quick?
Sure. Go
ahead.
So in terms of, for your rates of convergence, if you go to slide 14, that's the first rate of convergence that you showed, you have a square root of t there. So why is it square root of t? Because it's not strongly convex case?
Yeah, this is not for the strongly convex case, correct.
Okay, all your rates are the optimal rates, right? Like whatever case you consider for strongly convex.
Yeah, we do get optimal rates. That's right.
Okay, I promise not quick question. So my not quick question is, so you said how with the generalization in the second part of your talk, you can get the momentum update and so on. Can you explain how momentum update is a special case? I couldn't see it.
Okay. So momentum, let me try to give you intuitive, nice explanation. So in momentum, what you do is when you do one local SGD update, you store it in memory and then add a fraction of that update to the next update.
Correct.
So effectively, what will happen is like if you take this accumulated local update, this blue color arrow, it's a different linear combination of each of these gradients.
Mm-hmm.
When you do momentum. So because you're adding a fraction of an older gradient to the new gradient. So here, when I say momentum, the momentum buffer is reset every time you're doing a communication round.
I see.
So across rounds, we don't have any momentum buffer. At the beginning of the round, you reset the buffer to 0.
I see.
So that is actually something that we need in federated averaging because only a subset of the clients participate. So we don't want the clients to have some memory of previous rounds that can cause staleness issues.
So normally momentum gives you speed up, right? I know in SGD you can't beat 1 over t, but then it gives speed up in one of the terms relative to the other term and so on. So between this reset, do you still get that speed up or do you lose that speed up?
We do get that speed up even if you do the reset because locally, like for the local objective function, you will reach its minima faster.
I see. Okay, great. Thanks.
Okay. Any other not short questions? Thank you, everyone. Thanks for the attention. I know everybody's tired of listening to online talks in the pandemic. So thanks for attending mine, even though it was at the end of the academic year.
And have a great summer.
Thank you again, Gauri.
Bye, everyone.
Bye.